Quantum computers make headlines for qubit counts and speed records. The real bottleneck is quieter and harder. Noise. Every gate operation, every measurement, every microsecond of idle time, physical qubits drift, flip, and decohere. A machine with a million noisy qubits still cannot run a long, reliable calculation. Error correction is the engineering layer that turns fragile hardware into something you can trust. It is not a side feature. It is the difference between a physics demo and a useful computer. In 2026, every serious roadmap runs through it. Classical bits are robust. Copy them, check parity, fix a flipped zero. Qubits live in superposition and entanglement. Measuring them to check for errors destroys the very information you need. Environmental noise, heat, electromagnetic interference, imperfect control pulses, all inject errors faster than you think. Today's superconducting qubits might survive tens to hundreds of microseconds. Trapped ions last longer but face their own calibration demons. The hardware is improving. The fragility is fundamental. You cannot brute force past it. You must encode redundancy in a way quantum mechanics allows. Here is the core idea. A physical qubit is the actual device on the chip. A logical qubit is an encoded state spread across many physical qubits so errors can be detected and fixed without collapsing the computation. Think of it like RAID for quantum memory, except the parity checks obey the rules of quantum mechanics. One protected logical qubit might require hundreds or thousands of physical qubits once you account for the full error correction stack. That overhead is why qubit count press releases mislead. The number that matters is logical qubits with low enough error rates to finish real algorithms. The leading architecture in 2026 is the surface code and its stabilizer cousins. Qubits sit on a two-dimensional lattice. Neighboring qubits share entanglement. Ancilla qubits measure syndromes, patterns that reveal where an error occurred, bit flip, phase flip, or both, without directly reading the protected data. Classical control electronics interpret those syndromes and apply corrective gates. Google, IBM, and research labs worldwide publish progress on distance 3, distance 5, and larger code demonstrations. The surface code is not the only approach. But it is the one most hardware teams bet on because it tolerates local errors and maps cleanly onto grid-like qubit layouts. Watch the cycle. Encode information into a logical qubit. Run computation steps. Periodically pause to measure stabilizer operators. If syndromes flag an error, apply a correction. Repeat thousands of times per second. The magic is that syndrome measurement extracts just enough classical information to fix the qubit without learning the secret quantum state. Get the timing wrong and you introduce more errors than you remove. Get the connectivity wrong and the code distance collapses. This is why control systems, cryogenics, and classical coprocessors are as important as the qubit itself. Error correction is a full-stack sport. Now the uncomfortable math. Early fault-tolerant estimates suggested you might need 1,000 physical qubits or more per logical qubit, depending on error rates and algorithm depth. Better hardware shrinks that ratio, but overhead remains enormous. A useful chemistry simulation might demand hundreds of logical qubits. Multiply by the physical overhead and you see why the industry obsesses over every basis point improvement in gate fidelity. Error mitigation tricks, zero-noise extrapolation, probabilistic error cancellation, help on near-term machines. They are not replacements for full correction. They are bridge tools while the lattice scales up. What is live in 2026? Live 1, repeated demonstrations of error detection and correction below the break-even threshold on superconducting and trapped ion platforms. Live 2, roadmaps from major vendors explicitly targeting logical qubits this decade, not just raw qubit counts. Live 3, hybrid workflows where error mitigation extends today's noisy machines while correction hardware matures. Not live yet, large-scale fault-tolerant machines running Shor's algorithm on production data. That is still years out on conservative timelines. Your move, watch logical qubit announcements, not just chip size. Track syndrome error rates in published papers. That is the scoreboard. Tune in tomorrow, we unpack fault-tolerant quantum computing, what changes once error correction actually wins. Subscribe if you want the future without the fluff.